Welcome back to the Sleepy Science Channel. Tonight we're drifting toward a neighbor, a world that sits just beyond our own in the cosmic neighborhood. Mars waits there in the darkness, patient and quiet, wearing its dusty red coat. It's been watching us for as long as we've been watching it. This rusty sphere has sparked more dreams and questions than perhaps any other object in our solar system. Writers imagined civilizations on its surface. Scientists wondered if life once bloomed there. Explorers sent machines across millions of miles just to touch its soil. Mars holds mysteries in its canyons and secrets beneath its frozen caps, and tonight we'll wander through them together, one gentle fact at a time. If these peaceful journeys through science bring you comfort, perhaps you'll share this channel with someone who might need the same calm, or leave a kind word below. It helps more than you might think. But there's no pressure. Just close your eyes when you're ready. Breathe slowly, and let Mars carry your thoughts somewhere peaceful. Shall we begin? The distance between Earth and Mars changes constantly as both planets orbit the Sun. Sometimes Mars feels close. Other times it drifts far away. At their nearest approach, called opposition, the two worlds come within about 34 million miles of each other. That might sound like a vast gulf, and it is. But in cosmic terms, it's practically next door. At their farthest, when the Sun sits between them, Mars and Earth can be separated by more than 250 million miles. This shifting distance happens because both planets follow elliptical paths around the Sun at different speeds. Earth completes its orbit in 365 days. Mars takes 687 Earth days to finish one slow lap. They play a constant game of catch-up, sometimes racing side by side, sometimes drifting to opposite ends of the solar system. For mission planners, this dance matters enormously. Spacecraft launched during opposition windows can reach Mars in 7 months. Launched at the wrong time, and the journey stretches much longer. The planets align favorably about every 26 months, a rhythm written into the mechanics of their orbits. So Mars isn't just sitting there waiting. It's moving, wandering, drawing near, and pulling away like a friend who visits on their own schedule. Mars takes 24 hours and 37 minutes to complete one rotation. Here's something remarkable. A day on Mars feels almost identical to a day on Earth. Almost. While our planet spins completely around in 24 hours, Mars takes just slightly longer, 24 hours and 37 minutes to be exact. Scientists call this period a sol to distinguish it from an Earth day. But that extra 37 minutes is barely noticeable. If you stood on Mars, watching the Sun rise and set, the rhythm would feel familiar. Morning would arrive. Afternoon would stretch out. Evening would settle in. Night would deepen. All at a pace your body would recognize. Early Mars mission controllers even adjusted their schedules to Martian time, coming to work 37 minutes later each day. Their circadian rhythms slowly shifting to match the planet they were exploring. For weeks they lived on Mars time, while their bodies remained on Earth. It created a strange jet lag without ever leaving the building. But it worked. The similarity makes Mars feel less alien somehow. More like a place humans could actually inhabit, where the cycle of day and night wouldn't throw everything into chaos. Where you could wake with the sunrise and sleep under stars without completely rewiring your internal clock. Among all the planets, Mars offers us this one familiar comfort, a day that feels like home. The Martian atmosphere is incredibly thin compared to Earth's. Stand on the surface of Mars, and you'd be surrounded by air so sparse, it might as well be vacuum. The atmospheric pressure there measures less than 1% of what we experience at sea level here on Earth. It's roughly equivalent to standing 19 miles above Earth's surface. Far higher than any mountain, higher than most airplanes fly. At that altitude, our atmosphere becomes so thin that water would boil at room temperature. Blood would vaporize. Survival without a pressurized suit becomes impossible within seconds. Mars offers that same hostile thinness at ground level. Its atmosphere exists, but barely. Composed mostly of carbon dioxide with traces of nitrogen and argon. There's almost no oxygen. Nothing a human could breathe. This wasn't always true. Evidence suggests Mars once held a thicker atmosphere, something denser and more protective. But over billions of years, solar wind stripped it away. Without a strong magnetic field to shield it, the atmosphere simply bled into space. What remains is a whisper of what once was. Too thin to hold much heat, too weak to block radiation, yet still present enough to create weather, to carry dust storms across entire hemispheres, to form thin clouds and morning frost. The Martian atmosphere is a ghost of its former self, faint but not entirely gone, still clinging to the planet like a memory. Temperatures on Mars swing wildly between day and night. That thin atmosphere can't hold heat the way Earth's does. During a summer day at the equator, temperatures might climb to a relatively pleasant 70 degrees Fahrenheit. Warm enough that if you had breathable air and radiation protection, you could walk around in shirt sleeves. But as soon as the sun sets, everything changes. Without a thick atmosphere to trap warmth, the heat radiates straight back into space. Temperatures plummet. By the middle of the night, that same equatorial region might drop to -100 degrees Fahrenheit. A swing of more than 170 degrees in a single sol. Near the poles, it gets even more extreme. Winter temperatures can fall below -220 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the atmosphere, creating dry ice caps that grow and shrink with the seasons. These wild fluctuations mean Mars experiences temperature ranges Earth can barely match. Our thick atmosphere acts like a blanket, moderating extremes, spreading heat around. Mars has no such protection. The planet shifts between extremes, with nothing to soften the transition. It's a world of harsh contrasts, scorching, sun-baked afternoons, followed by bitterly frozen nights, where the environment can shift from almost comfortable to lethally cold in just a few hours. Mars has the largest volcano in the entire solar system. Rising from the Martian surface like a monument to ancient geological fury stands Olympus Mons, the tallest volcano we've ever discovered. It towers roughly 16 miles high. That's nearly 3 times the height of Mount Everest. If you could somehow place Olympus Mons on Earth, it would pierce through most of our atmosphere. Airplanes cruise at about 6 miles up. This volcano would rise far beyond them. But height is only part of its grandeur. Olympus Mons stretches roughly 374 miles across, wider than the entire state of Arizona. Its base is so broad that if you stood at its center, you couldn't see the edges. They would lie beyond the horizon. The slopes are gentle, though, rising at an average of only 5 degrees. You could hike up them without realizing you were climbing a mountain until you looked back and saw how far you'd risen. This massive shield volcano formed over millions of years. Lava flowed repeatedly from the same spot. Each eruption added another layer, building slowly upward. On Earth, tectonic plates move beneath volcanoes, carrying them away from their magma source. That's why Hawaiian volcanoes form chains. But Mars has no plate tectonics. Its crust stays still. So Olympus Mons sat over its hotspot for eons, growing larger with each eruption. The result is a structure so enormous it defies easy comprehension. A sleeping giant that hasn't erupted in millions of years, but still dominates the Martian landscape. The Valles Marineris canyon system dwarfs Earth's Grand Canyon. Near the equator of Mars runs a scar so vast it makes Earth's grandest geological features look modest. Valles Marineris stretches roughly 2,500 miles across the Martian surface. If you placed it on Earth, it would span the entire width of the United States. From New York to Los Angeles, this canyon would cut across the continent. In places, it yawns 4 miles deep, more than 4 times the depth of the Grand Canyon. And it spreads up to 125 miles wide. Stand on one rim, and the opposite side would be lost in haze and distance. Scientists aren't entirely sure how Valles Marineris formed. It likely started as a crack in the crust caused by volcanic activity in the nearby Tharsis region. As lava piled up, building massive volcanoes, the weight may have stressed the surrounding crust until it fractured. Then, erosion took over. Water may have flowed through it. Wind certainly did. Landslides carved away at the walls. Over billions of years, these forces widened and deepened the initial crack into the tremendous canyon we see today. The scale is difficult to grasp. You could fit multiple Grand Canyons inside portions of it. Some sections contain layered rock walls that tell stories of different geological eras, each stripe a chapter in Martian history. To stand at the edge of Valles Marineris would be to confront the raw power of planetary geology, a reminder that worlds can tear themselves open, that surfaces we think of as solid are actually fragile, constantly shaped and reshaped by forces operating over timescales we can barely imagine. Water ice exists at both Martian poles. At the very top and bottom of Mars rest permanent ice caps, gleaming white deposits that grow and shrink with the seasons. They're not quite like Earth's polar ice, though. During Martian winter, each pole becomes buried under a seasonal layer of frozen carbon dioxide. Dry ice forms from the atmosphere as temperatures plummet. This temporary cap can be several feet thick, bright and reflective. But underneath that seasonal layer lies something more familiar: water ice, lots of it. The northern polar cap contains water ice mixed with dust and sits exposed during summer. The southern cap also holds water ice beneath its dry ice covering. Scientists estimate these polar deposits contain enough frozen water to cover the entire planet in a layer 35 feet deep if it all melted. That's a substantial reserve. Evidence that Mars once had abundant water. Much of it is now locked away in these frozen vaults, waiting, preserved. The ice sits there through Martian years, through dust storms and solar cycles. A reservoir of the planet's watery past, frozen into stillness. For future human visitors, these polar caps might prove invaluable. Water for drinking, for growing food, for creating breathable oxygen and rocket fuel. The ice represents possibility, a resource that could sustain exploration. For now, though, it simply endures, silent and frozen under thin skies. Ancient river valleys cut across much of the Martian surface. Look closely at Mars through a powerful telescope, or examine images from orbiting spacecraft, and you'll notice something striking. The surface is carved with channels, valleys, networks of tributaries that branch and merge like Earth's rivers. These aren't rivers anymore, they're bone dry. But the shapes they left behind tell a story. Water flowed here once, lots of it. Some valleys stretch hundreds of miles, winding through highlands and lowlands, creating patterns that could only form from sustained flowing liquid. Rain might have fed them, or perhaps groundwater seeping up, or massive floods released from beneath the surface. The details remain debated, but the conclusion is clear. Mars was once a much wetter world. The channels concentrate in ancient terrain, regions billions of years old, which suggests Mars lost most of its water early in its history. These dry riverbeds are fossils of a different era, when the atmosphere was thicker, when temperatures stayed warm enough for liquid water to persist on the surface, when storms might have swept across continents and rain might have pattered against rocks. Imagining that Mars feels like imagining a different planet entirely. Yet the evidence sits there in the geology, undeniable. The rivers are gone, but their ghosts remain, etched permanently into the landscape. A record written in stone of water that flowed and vanished billions of years ago. Scientists have found strong evidence that liquid water once filled ancient lakes on Mars. Among the most compelling discoveries are the remains of what clearly were once lakes. Gale Crater, where the Curiosity rover landed, shows layered sediments that could only have formed underwater. Fine particles settling slowly in still water, building up over time into distinct bands. The rover found rounded pebbles too, the kind that form when flowing water tumbles rocks smooth. It detected minerals that form only in the presence of water. Clay minerals, sulfates, chemical signatures of an ancient aquatic environment. Jezero Crater, where the Perseverance rover now explores, shows even clearer evidence. A river once flowed into this crater carrying sediment that formed a delta. Just like river deltas on Earth, where the Mississippi meets the Gulf of Mexico or the Nile spreads into the Mediterranean. The shapes are unmistakable, finger-like deposits reaching into what was once a lake bed. Perseverance is currently collecting samples from this ancient delta, looking for any traces of past life that might have lived in those waters. These weren't small puddles. Some of these ancient lakes may have been hundreds of feet deep, persisting for thousands or even millions of years, long enough for ecosystems to potentially develop, long enough for complex chemistry to occur, long enough for life to gain a foothold if conditions were right. The water is gone now, evaporated or frozen underground, but the evidence of its presence remains clear. Mars once held lakes, possibly even seas. It was a world where water pooled and flowed and shaped the land. Recurring slope linea hint that liquid water might still flow seasonally on Mars. Even today, Mars might have fleeting moments of flowing water. Scientists discovered strange dark streaks that appear on steep slopes during warm seasons and fade during cold ones. They named them recurring slope lineae. These features show up on sun-facing slopes where temperatures climb above freezing. As Martian spring and summer warm the surface, these dark lines gradually extend downhill, sometimes growing several hundred feet long. When winter returns, they fade away. The pattern repeats year after year in the same locations. What causes them? The most likely explanation involves briny water, salty enough that it remains liquid at temperatures well below the freezing point of pure water. Perchlorates, salts found in Martian soil, could lower the freezing point significantly. Underground ice might melt slightly when warmed. The brine seeps out, flows downslope, then evaporates or refreezes, leaving behind the dark stain. The evidence isn't conclusive yet. Some scientists think it could be dry granular flows instead, dust and sand moving downhill without any water at all. But the seasonal timing and the locations where these features appear strongly suggest liquid brine. If true, it means Mars isn't completely dry. Water still moves there, not rivers or lakes anymore, just tiny trickles of salty moisture briefly flowing before disappearing again, fragile and fleeting. But there nonetheless, a whisper of the planet's watery past still clinging to life. Mars has two small moons that likely formed elsewhere. Orbiting close to Mars are two tiny moons, Phobos and Deimos. Neither looks like our moon. They're irregular, lumpy shapes, more like captured asteroids than proper spheres. Phobos measures about 14 miles across at its widest. Deimos even smaller at roughly 8 miles. Both are dark, covered in a layer of dust and craters. Their surfaces look ancient and battered. Scientists believe these moons didn't form alongside Mars the way our moon formed with Earth. Instead, they probably originated in the asteroid belt between Mars and Jupiter. Sometime in the distant past, Mars's gravity caught them, pulled them into orbit, and they've been circling ever since. Phobos orbits incredibly close, only about 3,700 miles above the Martian surface. That's closer than some satellites orbit Earth. From Mars's surface, Phobos would appear to zip across the sky, rising in the west and setting in the east, completing an orbit in just over 7 hours. It moves so fast relative to the planet's rotation that it appears to move backward compared to the stars. Deimos orbits farther out, taking 30 hours to complete one loop. From the surface, it would look like a bright star slowly drifting across the sky. Both moons are doomed eventually. Phobos is gradually spiraling inward. In about 50 million years, it will either crash into Mars or break apart from tidal forces, forming a temporary ring around the planet. Deimos, meanwhile, is slowly drifting away. Eventually, it might escape Mars's gravity entirely. For now, though, these two irregular companions keep their silent watch, remnants from the asteroid belt, prisoners of Martian gravity. Phobos rises and sets multiple times in a single Martian day. Because Phobos orbits so close and so fast, anyone standing on Mars would witness something impossible on Earth. This moon rises in the west and sets in the east, backward from what we're used to, and it does this multiple times each sol. Phobos completes roughly 3 orbits for every Martian day. So if you were watching from the surface, you might see it rise in the west, arc across the sky in just over 4 hours, set in the east. Then, a few hours later, watch it rise again. This strange ballet happens because the moon moves faster than the planet rotates. Imagine standing on the equator of Mars at sunset. The sun sinks below the western horizon. Darkness settles in. Then, a few hours later, Phobos climbs into view from the west. A lumpy, potato-shaped object visible to the naked eye. Much larger in appearance than Deimos, but still only about 1/3 the size our moon appears from Earth. It crosses the entire sky in about 4 hours and 20 minutes, then dips below the eastern horizon. If you stayed awake through the night, you might see it rise and set twice more before the sun returns. This rhythm would feel profoundly strange to human colonists. A moon that doesn't follow the rules, that races overhead instead of drifting slowly, that treats the sky like a racetrack. Deimos behaves more predictably, rising in the east and setting in the west like our moon, taking about 2.5 sols to complete its leisurely journey across the Martian sky. Between them, these two moons create a night sky unlike anything Earth offers. One moon sprinting, one strolling, both forever circling their rusty parent world. Dust storms on Mars can engulf the entire planet. Mars is famous for its dust storms. Some are local, swirling devils of dust that spin across the surface like tornadoes. But others grow into something far more impressive. Regional storms can cover areas the size of continents, and occasionally, conditions align perfectly for a global dust storm, one that wraps the entire planet in a haze so thick it blocks out the sun. These planet-wide storms don't happen every year. They're rare, occurring roughly once every 3 to 4 Martian years. But when they do develop, they're spectacular. The storm begins somewhere in the southern hemisphere during spring or summer. Dust, lifted by winds, begins to absorb sunlight. This heats the air around it, which creates more wind. More wind lifts more dust. More dust heats more air. The cycle feeds on itself. Within weeks, the storm can spiral out of control, spreading across hemispheres, turning the entire sky orange-brown. The dust hangs suspended for weeks or even months before finally settling. During the 2018 global dust storm, the Opportunity rover lost contact with Earth. Solar panels couldn't generate power through the darkness. The little robot went to sleep and never woke up. The storm eventually cleared, but by then winter had arrived and Opportunity's batteries had drained. For spacecraft orbiting Mars, these storms are both beautiful and ominous. Beautiful because they demonstrate the power still alive in Mars's thin atmosphere. Ominous because they remind us how hostile the environment remains. Even without much air, Mars can still whip that air into fury, burying everything in dust, blocking out light, creating conditions that would challenge any human settlement. The sky on Mars appears butterscotch during the day due to dust. If you stood on the surface of Mars and looked up during the day, you wouldn't see the deep blue we enjoy on Earth. Instead, the Martian sky glows a soft butterscotch color, sometimes peachy orange, sometimes pale yellow-brown. The exact shade shifts depending on how much dust hangs in the air. But it's never blue. This happens because of the fine dust constantly suspended in the thin atmosphere. On Earth, our thick atmosphere scatters blue light more than other colors. That's why we see blue overhead. But Martian dust particles are just the right size to scatter red and orange wavelengths. The sun's light passes through billions of these tiny particles, and the red end of the spectrum bounces around while blue light passes straight through. The result is that warm, peachy glow. Around sunset and sunrise, the effect reverses somewhat. Near the horizon, the sky takes on a bluish tint, while the area around the sun glows red and orange. It's the opposite of Earth's sunsets. Here our sunsets blaze orange and red because sunlight passes through more atmosphere at that angle. On Mars, the dust scatters so much red light during the day that by sunset, only the blue wavelengths remain prominent near the sun. Rovers have captured these eerie sunsets, the sun appearing smaller because Mars orbits farther from it, sinking toward the horizon with a bluish haze around it. Above that, the sky transitions back to its dusty orange, strange and beautiful. A reminder that even something as simple as sky color changes from world to world. Mars experiences seasons just like Earth does. Tilt matters. Earth's axis tilts about 23.5 degrees relative to its orbital plane. That tilt gives us seasons. When the northern hemisphere leans toward the sun, it's summer there. When it leans away, it's winter. Mars has a similar tilt, about 25 degrees. So it too experiences seasons: spring, summer, autumn, winter, in each hemisphere. As Mars orbits the sun, its northern hemisphere tilts toward our star for part of the year. Temperatures warm. The polar ice cap shrinks. Dust storms become more common. Then, as Mars continues around its orbit, the northern hemisphere tilts away. Winter arrives. Temperatures plummet. Carbon dioxide freezes out of the atmosphere and accumulates at the pole. Meanwhile, the southern hemisphere goes through its own seasonal cycle. But there's a twist. Mars's orbit is more elliptical than Earth's. It's not a perfect circle. This means Mars moves closer to and farther from the sun during its year. When the southern hemisphere tilts toward the sun during its summer, Mars happens to be near its closest approach. So southern summers are shorter but more intense, warmer, more prone to violent dust storms. Northern summers, by contrast, occur when Mars is farther from the sun. They're longer but milder. This creates an asymmetry. The seasons in each hemisphere don't quite mirror each other. Southern spring and summer together last about 6 Earth months. Northern spring and summer stretch to almost 9. This lopsided calendar affects everything from dust storm patterns to ice cap behavior. Mars's seasons follow the same basic principle as Earth's, but with their own unique rhythm, shaped by tilt and orbit into something familiar yet distinctly alien. The Martian year lasts 687 Earth days. One trip around the Sun takes Mars nearly twice as long as it takes Earth. While we complete our yearly journey in 365 days, Mars needs 687 Earth days to finish one orbit. That's roughly 1 year and 10 months by our calendar. This happens because Mars orbits farther from the Sun. Its path stretches wider, and objects farther from the Sun move more slowly due to weaker gravitational pull. So everything on Mars operates on this extended timeline. A Martian year contains about 669 sols, those slightly longer Martian days. The seasons unfold slowly. Spring doesn't arrive for months. Summer stretches on. Autumn takes its time. Winter settles in for what feels like an eternity. For anyone living on Mars, this elongated calendar would reshape how they think about time. Birthdays would come less frequently. Children would age more slowly in Martian years. A 10-year-old on Earth would only be about 5 in Martian years. Mission planners have to account for this too. A 2-year mission on Mars actually spans nearly 4 Earth years. Supplies have to last. Equipment has to endure. The extended timeline affects everything. But it also means more time to explore, more time to discover, more time to understand this neighboring world that moves through space at its own unhurried pace. Mars's gravity is about 38% of Earth's. Step onto the surface of Mars and immediately you'd notice something different. You'd feel lighter, much lighter. If you weigh 150 pounds on Earth, you'd weigh only about 57 pounds on Mars. That's because Mars has less mass than Earth and a smaller radius. Gravity depends on both those factors. Less mass means less gravitational pull. Stand on Mars, and you could jump nearly 3 times as high as you can here. A simple hop might lift you several feet off the ground. Walking would feel bouncy, almost like moving on a trampoline. You'd have to relearn basic movements, how much force to use when stepping, how to catch yourself when you stumble, how to lift and carry objects that suddenly weigh a fraction of what you expect. This reduced gravity has implications for long-term human health, though. Our bodies evolved under Earth's pull. Our bones' density, our muscle mass, our cardiovascular system, all calibrated for one standard gravity. Spend months or years in Mars's weak gravity, and your bones would begin to lose calcium. Your muscles would weaken. Your heart wouldn't have to work as hard, so it would shrink slightly. Astronauts on the International Space Station experience similar effects in microgravity. They exercise for hours each day to counteract bone and muscle loss. Mars colonists would need similar regimens. The lighter gravity might feel fun at first, liberating even. But over time it presents serious challenges. Still, it's far better than zero gravity. And it's enough to keep objects firmly on the ground, to allow liquids to pour, to create a sense of up and down. Mars offers a compromise. Not quite Earth, but not the floating weightlessness of space either. The Martian soil contains toxic perchlorates. Bring a handful of Martian soil into a laboratory and analyze it carefully, and you'll find something concerning: perchlorates. These are chemical compounds containing chlorine and oxygen. They exist naturally on Earth too, but only in tiny trace amounts in certain dry regions. On Mars, they're everywhere, concentrated in the soil at levels high enough to be dangerous. Perchlorates interfere with thyroid function in humans. They're toxic if ingested, and they make the soil itself hostile to most Earth life. This discovery complicated dreams of growing food on Mars. You can't just scoop up Martian dirt and plant seeds in it. The perchlorates would kill the plants or contaminate any crops that manage to grow. Any future Martian farmers will need to either wash the perchlorates out of the soil or bring clean growing medium from Earth, or perhaps grow food in sealed hydroponic systems. None of these solutions are simple. All add weight, complexity, cost. But the perchlorates aren't entirely bad news. They could actually be useful. These compounds can be broken down to release oxygen, which astronauts could breathe. They can also provide fuel. With the right processing, perchlorates could help sustain a human presence. They're a resource and a hazard simultaneously. This duality defines much of Mars. What seems like an obstacle often contains hidden potential. The planet challenges us to be creative, to solve problems, to find ways to turn hostile chemistry into useful tools. No magnetic field protects Mars from solar radiation. Earth has something precious, a magnetic field, generated deep in our planet's core, where molten iron swirls and flows. This field extends far into space, creating an invisible shield that deflects charged particles from the sun. Solar wind streams toward us constantly, but most of it gets diverted around our magnetic bubble. We barely notice. Mars once had a magnetic field too. Evidence in ancient rocks shows that billions of years ago, the planet's core generated magnetism just like Earth's. But then, something changed. The core cooled, solidified. The churning that created the magnetic field slowed and stopped. And without that protection, Mars became vulnerable. Solar wind now strikes the Martian atmosphere directly. Over billions of years, it stripped away much of that atmosphere, blowing it into space. What remains offers no real shielding. Stand on the surface of Mars, and you'd be exposed to radiation levels far higher than anything on Earth. Cosmic rays, solar particles, all raining down constantly. Not enough to kill you instantly, but enough to dramatically increase cancer risk over time, enough to damage DNA, enough that any human settlement would need heavy shielding, underground habitats, thick walls, or perhaps structures built into lava tubes and caves. The lack of a magnetic field shapes what's possible on Mars. It's why the atmosphere is thin, why the surface is so harsh, why protection becomes essential. Yet it's also a reminder of planetary evolution, that worlds change, that what once was can be lost. Mars had protection and lost it. Now it faces the cosmos unshielded. Ancient lava tubes on Mars might provide natural shelter. Beneath the surface of Mars lie tunnels, not made by flowing water, but by flowing rock. Lava tubes form when molten lava flows beneath a cooling crust. The surface solidifies, while liquid rock continues moving underneath. Eventually, the lava drains away, leaving behind a hollow tunnel. Earth has lava tubes, especially in volcanic regions like Hawaii. But Martian lava tubes could be enormous. Mars' lower gravity meant lava could flow farther before solidifying. It could create larger caverns. Some scientists estimate that Martian lava tubes might be hundreds of feet wide, big enough to shelter entire settlements. These tubes offer several advantages. They're naturally shielded from radiation. Several feet of rock overhead would block harmful particles. They maintain more stable temperatures than the surface, protected from the wild day-night swings. And they're shielded from dust storms. The storms that occasionally darken the entire planet wouldn't penetrate underground. For future explorers, these tubes represent ready-made habitats. No need to build walls or roofs. Just move in. Seal the entrances. Pressurize the interior. Add life support systems and living quarters. Instant protection. Orbital images show promising collapse pits. Places where the roof of a lava tube has fallen in, creating a skylight into the tunnel below. Rovers haven't explored these yet, but they're on the list. Understanding these formations could be key to human survival on Mars. Natural caves and tubes scattered across the planet, waiting, empty, ready to provide shelter. The Curiosity rover has been exploring Mars since 2012. On August 6, 2012, a car-sized robot named Curiosity touched down in Gale Crater. It arrived via an elaborate sky crane maneuver, lowered on cables from a hovering descent stage. The landing was so complex, engineers called it 7 minutes of terror. But it worked. Curiosity's wheels settled gently onto Martian soil, and it's been exploring ever since. More than a decade of continuous operation, far beyond its original 2-year mission. Curiosity carries a full suite of scientific instruments, cameras, a laser to vaporize rocks from a distance and analyze the vapor, a drill to collect samples, a chemistry lab on board to study those samples in detail. Its mission has been to determine whether Mars ever had conditions suitable for life. And the answer it found is yes. Gale Crater once held a lake. The rocks contain minerals that form in water. Organic molecules exist in the samples, not evidence of life itself, but the building blocks. The chemistry is there. The environment was once habitable. Curiosity has climbed partway up Mount Sharp, a mountain sitting in the center of Gale Crater. Each layer it passes represents a different era in Martian history. Like reading a geology textbook written in stone, the rover has driven over 17 miles, taken hundreds of thousands of images, survived dust storms, endured radiation. Its nuclear power source will keep it running for years. Yet, slowly, patiently, it continues upward, studying each layer, sending data home, teaching us what Mars once was and what it might still be. Perseverance is currently searching for signs of ancient life. In February 2021, another rover landed. Perseverance, larger and more advanced than Curiosity. It touched down in Jezero Crater, a location chosen specifically because it once held a lake fed by a river. That river deposited sediment into the lake, creating a delta. Deltas are excellent places to look for signs of ancient life. Organic material gets trapped in the sediments, preserved over billions of years. Perseverance carries instruments designed to search for biosignatures, chemical or physical signs that life once existed. It has a drill to collect core samples. These samples are being carefully sealed and cached, left on the surface for a future mission to retrieve and bring back to Earth. That sample return mission is still being planned, but if it succeeds, scientists will be able to study actual Martian rocks in laboratories here, with equipment far more sophisticated than anything we can send to Mars. That could finally answer the question of whether life ever emerged there. Perseverance also carries a small helicopter, Ingenuity, the first aircraft to fly on another planet. It was meant to make 5 test flights, prove that powered flight is possible in Mars's thin atmosphere. Instead, it flew over 70 times, scouting ahead, testing its limits, acting as an aerial scout, until eventually a rough landing damaged its rotors. But it succeeded beyond anyone's hopes, proving that future Mars missions can include aerial vehicles. Perseverance continues its work, drilling, sampling, caching, searching. Each rock it studies brings us closer to understanding whether we're alone. Mars once had a much thicker atmosphere billions of years ago. The Mars we see today is a shadow of what it once was. All the evidence points to a dramatically different planet in its youth. One with a thick atmosphere, perhaps as dense as Earth's, or denser. That thick blanket of gas would have created pressure, trapped heat, allowed liquid water to exist on the surface without immediately boiling away. Rivers flowed, lakes filled, rain might have fallen. The climate could have been remarkably Earth-like, at least in some regions, for hundreds of millions of years, maybe longer. During this ancient era, Mars might have been more hospitable to life than it is now. Warm, wet, protected. But then something changed. Scientists believe the planet's core cooled. The magnetic field shut down. Without that shield, solar wind began stripping away the atmosphere, ion by ion, molecule by molecule. Over millions of years, the thick protective envelope thinned, pressure dropped, temperatures fell, water froze, or evaporated, or soaked into the ground. The planet transformed from a world that might have cradled life into the cold, dry desert we see today. This transition happened gradually, not overnight, but it was inexorable. Today's thin atmosphere is a remnant, a ghost of what Mars once possessed. Studying this transformation helps scientists understand planetary evolution, how worlds live and die, how habitability can be gained and lost, and perhaps how we might prevent the same fate from befalling Earth. Some meteorites found on Earth actually come from Mars. Among the many rocks that fall from space and land on Earth, a rare few have an unusual origin. They're Martian, ejected from Mars millions of years ago by massive asteroid impacts, blasted into space, where they wandered through the solar system until Earth's gravity eventually captured them. We've identified over 200 Martian meteorites so far. We know they're from Mars because trapped inside are tiny bubbles of gas. And the composition of that gas matches perfectly the Martian atmosphere as measured by spacecraft. The ratio of different isotopes, the presence of specific noble gases. It's a chemical fingerprint, unique to Mars. These meteorites are incredibly valuable. They let scientists study actual pieces of Mars without going there. Some contain minerals that formed in water. Others show signs of volcanic activity. One famous Martian meteorite, ALH 84001, even sparked controversy in 1996. Scientists announced they'd found what might be fossilized bacteria inside, tiny structures that looked biological. The claim was hotly debated. Most scientists now think those structures formed through non-biological processes. But the debate highlighted how desperately we want to find life elsewhere, and how carefully we must examine every piece of evidence. These meteorites continue to yield discoveries. Each one is a free sample from Mars, a gift from deep time, a piece of another world that traveled millions of miles to land in our hands. The dream of terraforming Mars has captured imaginations for decades. Could we transform Mars into an Earth-like world? Make it warm, give it a breathable atmosphere, let liquid water flow on its surface. The idea is called terraforming, and it's been a staple of science fiction for generations. In theory, it might be possible. If you could warm Mars enough to release the frozen carbon dioxide from its polar caps and soil, that CO2 would thicken the atmosphere, create a greenhouse effect, trap more heat, which would warm the planet further, a positive feedback loop. Eventually, temperatures might rise enough for liquid water. You could introduce greenhouse gases engineered to be even more effective than CO2. Build enormous mirrors in orbit to focus more sunlight onto the poles, or even crash ammonia-rich comets into Mars to add both heat and atmosphere. But the challenges are staggering. Mars lost its atmosphere once because it has no magnetic field. Terraform it, and solar wind would slowly strip the new atmosphere away, too. Unless you could somehow restart the planet's magnetic field, which seems impossible with current technology, even if you solved that problem, the timescale would be immense. Centuries, maybe millennia. And the resources required would dwarf anything humanity has ever attempted. Still, the idea persists. Because Mars is close. Because it has water and resources. Because it's the most Earth-like planet within reach, some scientists argue we should preserve Mars as it is, study it in its natural state, search for indigenous life without contaminating it. Others see it as humanity's backup plan, a second home. The debate continues. But for now, Mars remains what it is, cold, dry, and waiting. Evidence suggests Mars experienced massive floods in its ancient past. Among the most dramatic features carved into Mars are enormous channels that clearly formed from catastrophic flooding, not gentle rivers that carved slowly over time. These are massive outflow channels, hundreds of miles long, miles wide, carved by unimaginable torrents of water that burst from underground. Scientists think subsurface ice melted rapidly, perhaps from volcanic heat. The water built up pressure beneath a frozen crust, then suddenly broke through, releasing floods that dwarfed anything Earth has ever seen. Water roared across the landscape at speeds that could fill Earth's Mediterranean Sea in a matter of weeks. The floods scoured the ground down to bedrock, carried house-sized boulders for miles, created islands and terraces and depositional fans, then drained away as quickly as they came, soaking into the soil, freezing, evaporating into the thin atmosphere. These catastrophic floods happened multiple times in Martian history. Different channels formed during different eras, some over 3 billion years ago, others more recently. Perhaps as recently as a few 100 million years. Though Mars looks dry now, these scars remind us of the violence water can unleash, of the power locked beneath a planet's surface, and of the dramatic transformations worlds can undergo. These channels are some of the clearest evidence that Mars was once a very different place. A world where water existed in quantities large enough to reshape continents in a matter of days. The Mars Reconnaissance Orbiter has mapped nearly the entire planet. Since 2006, the Mars Reconnaissance Orbiter has been circling the red planet, taking pictures, measuring temperatures, studying the atmosphere, mapping the surface in exquisite detail. Its camera can resolve features as small as a dining room table from orbit. It's photographed landing sites, tracked seasonal changes, watched dust storms develop and fade, found new impact craters that formed since it arrived. The orbiter has collected more data than all other Mars missions combined, hundreds of terabytes. Images, spectra, radar soundings. It carries an instrument that can peer beneath the surface using radar, revealing layers of ice and rock hidden from view. It's discovered vast deposits of subsurface ice, mapped the distribution of minerals, tracked where water ice sublimates from the surface during spring. This orbiter acts as a relay too. When rovers on the surface need to send data home, they often transmit it to MRO, which then beams it back to Earth with its more powerful antenna. Without this relay, the rovers would take much longer to return their findings. MRO has also scouted future landing sites, helping mission planners choose safe, flat areas, while also identifying scientifically interesting locations. After nearly 2 decades in orbit, the spacecraft is still functioning, still sending data, still watching over Mars. A silent sentinel studying every detail of the planet below. Olympus Mons stopped erupting millions of years ago, but might not be completely dead. That massive volcano hasn't erupted in a very long time. The youngest lava flows on Olympus Mons are estimated to be around 2 million years old, ancient by human standards, but recent in geological time. Some volcanic features might be even younger. The uncertainty comes from crater counting. Scientists estimate ages by looking at how many impact craters have accumulated on a surface. More craters mean older terrain. Fewer craters suggest younger flows. By this method, parts of Olympus Mons appear surprisingly fresh, which raises a question. Could it erupt again? No one knows for certain. The volcano could be extinct. Its magma source cooled and depleted, or it could merely be dormant, resting between eruptions. 2 million years is a long nap, but not unheard of for volcanoes. Some on Earth have waited longer between eruptions. If Olympus Mons is only dormant, it might wake someday, perhaps in another million years, perhaps sooner. There's no way to know without understanding what's happening deep beneath the Martian crust. Seismic monitoring could help, detecting any movement of magma or tremors that might indicate activity. The InSight lander placed a seismometer on Mars, but it was far from Olympus Mons and only operated for a few years. Future missions might deploy seismic networks across the planet, listening, watching for any signs of life deep below. For now, Olympus Mons sleeps, a giant that may or may not be finished writing its story. The thin atmosphere makes parachutes less effective for landing. Getting spacecraft safely to the surface of Mars is notoriously difficult. The atmosphere is thick enough to create heat during entry, so you can't ignore it. But it's too thin to slow a spacecraft down very much. Parachutes that would work perfectly on Earth are marginal on Mars. They help, but they can't do the whole job. Viking landers in the 1970s used parachutes plus retro rockets. Mars Pathfinder added airbags. It bounced across the surface before coming to rest. Spirit and Opportunity used the same technique. The Phoenix lander used rockets. Curiosity pioneered the Sky Crane, a hovering platform that lowered the rover on cables. Perseverance used the same method. Each mission has had to innovate, find new ways to shed velocity, to control descent, to touch down gently in an atmosphere that offers too little resistance. Engineers call it the 7 minutes of terror. The time between hitting the atmosphere and landing, during which the spacecraft is on its own. Radio signals take minutes to reach Earth, so there's no real-time control. Everything is automated, pre-programmed. The spacecraft has to execute a complex sequence perfectly. Any mistake means mission failure. The thin atmosphere also limits how much mass you can land. Heavier spacecraft need more parachutes, more fuel, more complexity. This puts a practical limit on the size of Mars landers. Until we develop completely different landing methods, there's a ceiling on how large a payload we can deliver, which affects everything from rover design to eventual human missions. Dust devils form frequently on Mars and can tower miles high. Watch the Martian surface for any length of time, and you'll eventually spot them. Dust devils, spinning columns of dust lifted by convection. They work the same way they do on Earth. Morning sun warms the surface, hot air rises. If conditions are right, the rising air begins to spin. As it whirls, it picks up dust from the ground. The dust makes the vortex visible, a graceful spiral climbing skyward. On Earth, dust devils are usually modest affairs, maybe a few dozen feet tall, lasting minutes before dissipating. On Mars, they can be enormous. Some tower several miles high, wide as football fields at the base. They can last for hours, marching across plains and crater floors. Rovers have photographed thousands of them, sometimes multiple dust devils visible at once, dancing across the landscape like desert spirits. They've even passed directly over rovers. Curiosity has detected the pressure drop as a dust devil swirled overhead. The rover's cameras have captured their shadows streaking across the ground. These vortices play an important role in Mars's climate. They lift dust into the atmosphere, That suspended dust affects temperature, scatters light, sometimes triggers larger storms. Dust devils also do something helpful. They clean solar panels. Spirit and Opportunity both benefited from dust devils sweeping past and blowing accumulated dust off their panels. Brief moments of natural housekeeping that extended their missions. Without those cleanings, the rovers would have lost power much sooner. So these spinning towers aren't just pretty, they're active participants in Martian weather. Sunrise and sunset happen more slowly on Mars because of the thinner atmosphere. When the sun rises or sets on Earth, the process feels relatively quick. The solar disk climbs or descends at a steady pace. Twilight doesn't last too long. But on Mars, with its thin atmosphere, things are different. There's less air to scatter light, so the extended glow we see before sunrise and after sunset is much reduced. The transition from day to night happens faster in terms of that ambient light. Yet the sun itself appears to move more slowly. Why? Because Mars rotates at a different speed and you're farther from the sun. The sun's apparent motion across the sky is gentler. Combine this with the thin atmosphere, and you get sunrises and sunsets that feel drawn out in some ways, but abrupt in others. The sky darkens quickly once the sun drops below the horizon. But the sun's descent itself is leisurely. Rovers have captured these moments beautifully. The sun appearing as a smaller disk than we see from Earth, about 2/3 the size, sinking toward a dusty horizon, creating that strange blue halo around it while the rest of the sky glows butterscotch. It's a sight no human has witnessed in person yet. But someday, someone will stand on Mars and watch the sun set. See that blue glow with their own eyes. Feel the temperature plummet as darkness falls, and experience sunset on an alien world. The InSight lander detected Marsquakes, revealing Mars is still geologically active. For years, scientists wondered whether Mars was truly geologically dead. Volcanoes, dormant, no plate tectonics. Perhaps the interior had cooled completely. Then, in November 2018, NASA's InSight lander touched down on Mars carrying a seismometer, an incredibly sensitive instrument designed to detect vibrations in the ground, Marsquakes, if they existed. And they did. InSight detected over 1,300 seismic events during its mission. Most were small, barely perceptible tremors, but some were substantial. Magnitude 4 or greater, strong enough to shake the ground noticeably. These quakes revealed that Mars is not entirely quiet. Something is moving inside. Magma shifting perhaps, or the crust settling as the planet slowly cools. The quakes also let scientists peer into Mars's interior. Just like on Earth, seismic waves travel through different materials at different speeds. By measuring how long waves take to arrive from different quakes, you can map what's inside. InSight's data revealed that Mars has a crust thinner than Earth's in some places, a mantle, and a core that's larger and less dense than expected. Likely a liquid core, at least partially. Still churning even though it no longer generates a magnetic field. These discoveries rewrote our understanding of Mars' interior. It's not a cold, dead ball of rock. It's still active, still changing, just much more slowly and quietly than Earth. Carbon dioxide frost forms on Mars during winter nights. As temperatures drop during Martian winter nights, the atmosphere itself begins to freeze. Carbon dioxide, the main component of that thin air, turns directly from gas to solid, skipping the liquid phase entirely. It condenses as frost on the surface, coating rocks, filling shadows, creating a delicate white layer. In some regions, this frost is thick enough to create landscapes that look almost snowy. But it's not water ice, it's dry ice, carbon dioxide frozen solid. When the sun rises, the frost doesn't melt. it sublimates, turning directly back into gas, vanishing into the air. This daily cycle of freezing and sublimating happens throughout Martian winter. At the poles, the frost accumulates, building up layer by layer into seasonal caps. These can be several feet thick. They sit atop the permanent water ice caps, bright and reflective. During spring, the frost begins to disappear. Jets of gas burst through the ice, creating dark fans and spots visible from orbit. The sublimating CO2 carries dust with it, spraying it across the white surface, creating strange patterns, spiders and starbursts etched into the frost. These features fade as the frost disappears, but they're striking while they last, evidence of a cycle that repeats every Martian year. The atmosphere freezing out, then returning, a planet breathing in, slow motion. Future Mars missions may include sample return, bringing rocks back to Earth. For all the instruments we've sent to Mars, nothing beats bringing samples home, where we can study them with equipment too large or complex to send to another planet. NASA and ESA have been planning a Mars sample return mission for years. The architecture is ambitious. Perseverance is already collecting samples, drilling cores, sealing them in tubes, leaving some in caches on the surface. A future mission would launch a lander carrying a rocket, a Mars ascent vehicle. Rovers or a helicopter would collect those sample tubes, load them into the rocket. The rocket would launch, becoming the first launch from another planet. In orbit, a spacecraft would rendezvous with the container holding the samples, capture it, then begin the journey back to Earth. The whole campaign requires multiple launches, precise coordination, new technologies, and a lot of money. The timeline keeps shifting, but the goal remains: bring Martian rocks to Earth. Let scientists examine them in labs. Study them for biosignatures with tools that can detect the faintest hints of ancient life. Analyze their chemistry in detail, determine their age precisely. These samples could answer fundamental questions. Was there life on Mars? What happened to the atmosphere? How did the climate change? A few pounds of rock could rewrite our understanding of planetary science, of biology, of our place in the universe. So, despite the challenges, the mission remains a priority, because some questions can only be answered by holding the evidence in our hands. The largest impact crater on Mars is over 6,000 miles across. Most impact craters are relatively small, a few miles wide, perhaps a few dozen. Even the biggest seldom exceed 100 miles. But Mars has one structure that defies normal categories: the Borealis Basin, also called the North Polar Basin. It covers roughly 40% of the planet's surface, stretching over 6,000 miles across. If it's truly an impact crater, and most scientists think it is, then it's the result of a collision so massive it nearly destroyed the planet. Sometime during Mars's early history, an object roughly the size of Pluto may have slammed into the northern hemisphere. The impact would have excavated billions of tons of rock, created unimaginable heat, potentially melted much of the crust. It might have vaporized oceans if Mars had them at the time, sent shockwaves rippling around the entire world. The basin created by this impact forms the lowland northern plains, a region noticeably smoother and lower than the southern highlands. The boundary between them runs roughly along a great circle, tilted relative to the equator. This dichotomy between north and south has puzzled scientists for decades. Why is one hemisphere so different from the other? The giant impact hypothesis offers an explanation: one catastrophic event that reshaped half the planet. If true, it was one of the largest known impacts in the solar system's history. A collision that would have altered Mars's geology, its climate, its potential for life, everything. The planet survived, but it bears the scar still, a basin so vast it's hard to recognize as a crater at all. Mars's surface contains vast amounts of iron, giving it the red color. Break open a Martian rock, and you'll find iron inside. Lots of it. The planet's crust is rich with iron minerals. In the ancient past, when Mars had a thicker atmosphere and possibly liquid water on the surface, that iron reacted with oxygen. It rusted, just like iron rusts on Earth. Oxidation. The process created iron oxide. Rust, spreading across the surface, coating every rock, every grain of dust. Over billions of years, this rust accumulated, deepened, until the entire planet took on a reddish hue. The color isn't uniform everywhere. Some regions appear darker, others lighter. Certain areas show hints of gray or tan, but overall, the red dominates. It's so pervasive that even from Earth with a backyard telescope, Mars appears distinctly red. Ancient cultures noticed this, associated it with blood, with war, with fire. The color shaped how we thought about the planet long before we understood what caused it. Today, we know its chemistry, not mythology. But the effect remains striking. A whole world painted in shades of rust. That color tells a story of an atmosphere that once contained oxygen, of water that flowed and reacted, of a planet that went through changes. The red is evidence, a visible reminder written across billions of square miles. Mars wears its history on its surface for anyone to see. Martian polar ice caps show layered deposits revealing climate history. If you could slice through a Martian polar cap, like cutting a cake, you'd see layers, bright bands, alternating with darker ones. Each layer represents a different period of accumulation. Ice mixed with dust, deposited during a particular era. Then conditions changed. A different mixture was laid down. Over millions of years, these layers stacked up, creating a record. Scientists study these layers from orbit using radar and imaging. The patterns reveal cycles, times when ice accumulated heavily, times when it eroded. These cycles are driven by changes in Mars's axial tilt and orbital shape. Earth has similar cycles called Milankovitch cycles. They affect our ice ages. Mars experiences something comparable but more extreme. The planet's tilt can vary from about 15 to 35 degrees over timescales of hundreds of thousands of years. When the tilt is greater, the poles receive more direct sunlight during summer. Ice sublimates, gets transported to other latitudes. When the tilt is less, the poles stay colder. Ice accumulates. The orbital eccentricity, how elliptical the orbit is, also changes. These astronomical variations create climate cycles that Mars records in ice. Reading these layers is like reading tree rings. Each band a chapter. Scientists can trace patterns going back millions of years. Understanding past climates helps predict future ones. And it provides context for understanding the planet's long-term evolution. The ice caps aren't just frozen water. They're archives, libraries of climate data waiting to be fully deciphered. Some regions on Mars show patterns that resemble tree branches but are actually gas jets. In spring, near the Martian poles, something strange appears. Dark spots and streaks spreading across the bright carbon dioxide frost. From orbit, they look almost like vegetation, branching patterns spreading outward, trees or coral or roots. It's a striking sight, but they're not alive. These patterns form through a fascinating process. As spring arrives, sunlight penetrates the translucent layer of frozen CO2. It warms the darker ground underneath. The ground heats up. That heat causes the CO2 ice directly above it to sublimate, turn from solid to gas. But it's trapped under the remaining ice layer. Pressure builds. Eventually, the gas breaks through. Erupting like a geyser, the jet carries dust with it, dark material sprayed across the white frost. The gas escapes and dissipates, but the dust remains, creating those dark fans and streaks. Winds near the surface shape the patterns, sometimes creating branching structures, sometimes radial sprays. The effect repeats across vast areas of the polar regions. Thousands of these features appear each spring, then fade as the frost disappears. It's a dynamic process, seasonal, entirely geological, yet hauntingly organic-looking. Early observers thought they might be signs of life. Now we understand they're just CO2 sublimation. But they remind us how alien processes can mimic familiar patterns. How easy it is to see life where none exists, and how careful we must be when interpreting features on other worlds. The atmosphere is so thin that liquid water cannot exist on the surface. Pour water onto the Martian surface, and something strange would happen. It wouldn't pool, wouldn't flow like it does on Earth. The atmospheric pressure is so low below the triple point of water that liquid water isn't stable. Water exists either as ice or vapor, nothing in between. If you brought warm water and poured it out, it would immediately begin to boil. Not from heat, but from low pressure. The liquid would flash into vapor, freeze, or both simultaneously, creating a chaotic mix of ice crystals and escaping gas. This makes the ancient river valleys and lake beds all the more remarkable. For water to have flowed on the surface, Mars needed a much thicker atmosphere. Higher pressure, different conditions entirely. When that atmosphere thinned, water could no longer exist as a liquid. It froze into the ground, evaporated into the air, disappeared. Today, any water that emerges briefly as briny seeps immediately starts to evaporate or freeze. It can't last. This is one of the major challenges for future colonization. Water is essential. Mars has plenty of it locked in ice, but using it requires contained environments, pressurized habitats, sealed greenhouses. You can't have open bodies of water. You can't build canals or reservoirs exposed to the atmosphere. Everything has to be enclosed, protected. The thin atmosphere that makes Mars' sky that beautiful butterscotch color also makes basic hydrology impossible. Mars has been visited by more spacecraft than any planet except Earth. Humanity has been fascinated with Mars for decades, and we've sent proof of that fascination in the form of spacecraft. Dozens of them. Orbiters, landers, rovers, starting in the 1960s with early Soviet and American missions. Most failed. Mars earned a reputation as a spacecraft graveyard. Missions lost during launch, lost in transit, lost during landing. The success rate was dismal for years, but gradually we learned. Viking 1 and 2 succeeded in 1976, becoming the first landers to operate for extended periods. Mars Pathfinder and its tiny Sojourner rover landed in 1997, proving rovers could work. Then Spirit and Opportunity in 2004. Both far exceeded their planned 90-day missions. Opportunity lasted 15 years. Since then, the pace has accelerated. Phoenix, Curiosity, Insight, Perseverance, multiple orbiters from NASA, ESA, India, China, the UAE. Mars has become an international destination, a proving ground for planetary exploration. Each mission builds on the last, learning from failures, refining techniques, pushing capabilities. Today, we have a fleet of active spacecraft studying Mars, taking images, measuring weather, analyzing soil, searching for water, listening for quakes. All of this from a planet tens of millions of miles away. It's an extraordinary achievement. And it's just the beginning. More missions are planned, eventually crewed missions. Mars has gone from an unreachable dream to a place we visit regularly. Our constant robotic presence there represents one of humanity's greatest collective accomplishments. The Opportunity rover lasted over 14 years despite being designed for 90 days. When Opportunity landed in January 2004, engineers gave it 90 sols, 3 months. That was the design life. The solar panels would accumulate too much dust. Power would drop. The rover would succumb to the cold Martian nights. That was the expectation. Instead, Opportunity kept going. And going. It drove farther than any vehicle on another world, over 28 miles. It explored craters, climbed hills, found evidence of ancient water everywhere it looked, discovered blueberries, tiny iron-rich spherules that formed in water, examined layers of rock that told stories of Mars's wet past. The rover survived frigid winters, dust storms, technical glitches. Its longevity was partly luck. Dust devils cleaned the solar panels periodically, keeping power levels higher than expected. But it was also clever engineering, robust design, and careful operation by mission controllers. They nursed the rover through challenges, tilted it to catch more sunlight during winter, drove it to warmer slopes, managed power carefully. For 14 years, Opportunity was humanity's eyes on Mars. Then, in 2018, a global dust storm enveloped the planet. The sky went dark. Solar panels couldn't generate power. Opportunity sent a final transmission, then went silent. Engineers tried for months to re-establish contact, sending commands, listening, hoping. But the rover never responded. Eventually, NASA declared the mission complete. Opportunity had far exceeded every expectation, delivered science worth many times its cost, and captured hearts worldwide. When it finally stopped, people mourned. A little robot on Mars had become something more. A symbol of exploration, perseverance, the human drive to discover. Methane has been detected in the Martian atmosphere, sparking debates about its source. Among the many gases in Mars's thin atmosphere, scientists have detected methane. Not much, just a few parts per billion. But it's there. And that's interesting because methane shouldn't be. In the Martian environment, ultraviolet radiation from the sun breaks down methane relatively quickly. Within a few hundred years, any methane should be destroyed. Yet, we keep detecting it, which means something must be producing it, replenishing what gets destroyed. On Earth, most methane comes from biological sources: bacteria in soil, digestive systems of animals, decay of organic matter. Some comes from geological processes, volcanic activity, reactions between rock and water. Mars could have either source, or both, or something else entirely. The Curiosity rover detected methane spikes in Gale crater. Sudden increases, followed by drops back to baseline. These spikes suggest localized sources, something releasing methane periodically, but finding the exact source has proven difficult. The methane disperses quickly in the thin atmosphere. Trace amounts don't provide much information about origin. Some scientists think it could be ancient methane trapped in ice or rock, released when the ice melts or cracks. Others speculate about subsurface microbial life. Organisms living deep underground where conditions might be less harsh, producing methane as a byproduct. We don't know yet. The detection is real. The source remains mysterious. Future missions might solve this puzzle, drilling deep, sampling subsurface materials, or deploying sensors that can track methane to its source. Until then, it remains a tantalizing hint, a question mark hanging over Mars. The Ingenuity helicopter proved powered flight is possible in Mars' thin atmosphere. When Perseverance landed, it carried a small passenger, a helicopter named Ingenuity, weighing just 4 pounds. With rotor blades that spun much faster than helicopters on Earth, it was a technology demonstration. Can you fly in an atmosphere 1% as thick as Earth's? The challenge was significant. Thin air provides almost no lift. The rotors had to spin nearly 3,000 RPM, far faster than conventional helicopters. The blades had to be light but strong. The whole system had to be efficient because solar panels could only provide limited power. Engineers gave Ingenuity 5 test flights. Prove it works, then retire it. On April 19, 2021, Ingenuity lifted off, 3 meters up, hovered for 30 seconds, then landed, the first powered controlled flight on another planet. It worked, so NASA kept flying. Each flight pushed farther, higher, faster. Ingenuity scouted ahead for perseverance, photographed terrain from above, demonstrated aerial reconnaissance. It survived 72 flights, over 2 hours of total flight time, traveled miles across the Martian surface, far beyond its design parameters. Eventually, a rough landing damaged its rotor blades. It could no longer fly, but by then, it had proven the concept completely. Future Mars missions will include helicopters, maybe larger ones, capable of carrying instruments or even samples. Ingenuity opened a new dimension of exploration, showed us that Mars's sky isn't off limits, that we can move through it, see from above, access places rovers can't reach, all because a tiny helicopter took a chance and succeeded beyond anyone's wildest hopes. Mars experiences global dust storms about once every 10 Earth years. Most weather on Mars is local, dust devils, regional storms, nothing earth-shattering. But occasionally, conditions align perfectly and a storm grows out of control. It starts somewhere in the southern hemisphere during spring or summer. A regional dust storm lifts particles into the air. The dust absorbs sunlight, heats the atmosphere, creates winds. Those winds lift more dust. More dust means more heating. The feedback loop accelerates. Within weeks, the storm can encircle the planet. The atmosphere fills with dust from surface to high altitude. Sunlight dims. Surface temperatures drop. The storm becomes its own weather system. These global events don't happen every year. They're irregular. Sometimes a decade passes between them, sometimes less. The 2018 storm was particularly intense. It darkened the sky over opportunity, cutting off the rover's solar power, ending its mission. The 2001 global storm was also massive, studied extensively by orbiters. These storms can last months. Dust slowly settles, the atmosphere clears, conditions return to normal. But while they rage, the entire planet transforms. Mars becomes shrouded. Details on the surface vanish. Only the highest peaks poke through the haze. From orbit, the planet takes on a uniform peachy glow, featureless, like looking at a ball of dust. Scientists study these events to understand Martian meteorology. How do they start? Why do some storms go global while others stay regional? What triggers the transition? The answers lie in complex interactions between surface temperature, atmospheric dynamics, dust properties. Understanding these storms is crucial for future human missions. Because a crew caught in a global dust storm would face reduced solar power, poor visibility, possibly hazardous conditions, we need to predict them, or at least understand them well enough to prepare. Mars's moons are slowly spiraling toward different fates. Phobos is doomed. Its orbit is decaying. Every century, it drops about 6 feet closer to Mars. That might not sound like much, but over millions of years, it adds up. Tidal forces between Mars and Phobos cause this. The Moon raises a tiny tidal bulge on Mars. That bulge drags on Phobos, slowing it down. A slower orbit means dropping lower and lower. In about 50 million years, Phobos will reach its limit. Either it will crash into Mars, creating a spectacular impact, or more likely, it will cross something called the Roche limit, the distance where tidal forces overcome the Moon's own gravity. At that point, Phobos will break apart, shatter into fragments. Those fragments will spread out along Phobos's orbit, forming a ring around Mars. For a while, Mars would have rings like Saturn, though much smaller, less impressive. Eventually, those ring particles would fall to the surface, peppering Mars with small impacts. The whole process will take millions of years, but it's inevitable. Deimos faces a different fate. Its orbit is slowly expanding, drifting away from Mars. Eventually, it might escape entirely, leave the Martian system, become an independent asteroid, wandering the solar system. Or it might end up in a stable, distant orbit, forever circling but never returning close. These two moons captured from the asteroid belt are slowly being released, one to destruction, one to freedom. It's a reminder that nothing in space is permanent. Orbits change, moons fall, systems evolve. What we see today is just a snapshot in a process that unfolds over deep time. The color of Mars's sky changes depending on dust levels and time of day. We think of Mars's sky as butterscotch or peachy orange, and usually it is, but that color isn't constant, it shifts. During particularly clear periods after dust has settled out, the sky can appear lighter, almost yellowish. More dust in the air means a deeper orange or reddish tint. During global dust storms, the sky darkens, becomes a murky brown-orange, almost oppressive, the sun barely visible through the haze. Near the horizon, the sky often shows different colors than overhead. Blues and greens sometimes appear in certain atmospheric conditions, and as mentioned earlier, sunset creates that bizarre reversal. The sun surrounded by bluish hues, while the sky around it glows reddish. Time of day matters too. Early morning and late evening, when the sun is low, the light passes through more atmosphere. Scattering changes. Colors shift. High noon on a clear day might show the palest butterscotch. Dawn and dusk might bring deeper oranges or unusual tints. Rovers have captured this variability. Thousands of images showing the Martian sky in different moods, different lighting, each one slightly different. It's a reminder that even something as simple as sky color depends on so many variables. Dust, time, atmospheric conditions. Mars's sky is dynamic, ever-changing. No two moments quite the same. For future human visitors, that changing sky will be part of daily life, reading the weather by the color overhead, knowing when storms approach because the orange deepens, watching the sky the way desert dwellers on Earth watch for rain. Radar has revealed massive underground ice deposits at mid-latitudes. Mars's surface ice is obvious. Polar caps, exposed glaciers in some craters, but much more ice hides underground. Radar instruments on orbiters can penetrate the surface, sending pulses that reflect differently off ice versus rock. These radar studies have revealed extensive subsurface ice deposits, not just at the poles, but at mid-latitudes, regions where temperatures are less extreme. Some deposits start just a few feet below the surface. Others run deeper. Thick sheets of ice buried under layers of dust and rock. These deposits might be remnants of ancient ice ages, times when Mars's axial tilt was different, when ice accumulated at different latitudes. As the climate changed, dust buried that ice, preserving it. Some deposits contain nearly pure ice, kilometers thick, stretching for hundreds of kilometers. They're like glaciers, but hidden. Invisible to the eye, only detectable through radar. For future explorers, these subsurface ice deposits are incredibly valuable. They're accessible, easier to reach than polar ice. And they're widespread. A settlement at mid-latitudes could tap into these reserves, extract water, purify it, use it for life support, agriculture, fuel production. The ice is a resource we didn't fully appreciate until recently. Mars isn't just dry surface and distant polar caps. It's laced with frozen water, hidden beneath a thin veil of dust, waiting. Some scientists propose that Mars could host microbial life in subsurface aquifers. The surface of Mars is harsh, cold, dry, bathed in radiation, not a friendly place for life as we know it. But beneath the surface, conditions improve. Temperature stabilizes. Radiation can't penetrate rock, and there might be liquid water. We know ice exists underground. If geothermal heat warms some of that ice, it could melt, forming pockets of liquid water, aquifers, protected by kilometers of rock. On Earth, life thrives in similar environments, deep underground, in aquifers kilometers below the surface. Bacteria live in total darkness, feeding on chemicals, extracting energy from rock and water, not from sunlight. These extremophiles show that life doesn't need surface conditions. It just needs liquid water, energy, and the right chemistry. Mars might offer all three in subsurface environments. We can't explore these depths yet. Our rovers scratch the surface, drill down inches or feet, not miles, but future missions might try, drilling deeper, sampling groundwater, looking for signs of life. If Martian microbes exist, they're probably hidden, living slowly, in isolated pockets, possibly unaware the surface world exists. Completely separate from the dead landscape above, finding them would require patience, technology, and luck. But it's possible. Life might be down there, quiet, persistent, waiting to be discovered. The idea keeps scientists hopeful, keeps missions focused on drilling, on sampling, on looking deeper than we've ever looked before. Ancient impact craters show signs of hosting lakes billions of years ago. When asteroids struck ancient Mars, they created craters. Some of these craters, filled with water, became lakes. We can see evidence of this in the geology. Layered sediments inside craters, deltas where rivers flowed in, minerals that form in standing water. Some of these crater lakes were small, temporary, filled during wet periods, dried out during droughts. Others persisted for much longer, perhaps millions of years, long enough for thick sediment layers to accumulate, long enough for complex chemistry to occur. These crater lakes are now prime targets for exploration, because if life ever existed on Mars, it likely needed standing water, stable environments, nutrients washed in from surrounding terrain. Crater lakes provided exactly that. They were isolated systems, little worlds contained within stone walls, each one a potential habitat. Jezero Crater, where Perseverance now roams, is one such ancient lake. The delta visible from orbit shows where a river delivered sediment. That sediment likely contains organic molecules, maybe even biosignatures, fossils, chemical traces. The rover is systematically sampling this delta, collecting cores, sealing them, leaving them for future retrieval. Each sample is a window into an ancient, aquatic environment. A chance to answer the question, did life emerge in these crater lakes, or was Mars always lifeless? The rocks hold the answer. We just need to bring them home and ask. Mars has fewer large impact craters than the Moon because of erosion. Look at the Moon and you'll see craters everywhere, large and small, overlapping, covering nearly every surface. Mars has craters too, but relatively fewer large ancient ones. Why? Because Mars has an atmosphere, thin as it is, and that atmosphere creates weather, wind, dust storms. Over billions of years, wind erosion wears down crater rims, fills in craters with blown dust, softens their features until they're barely recognizable. The Moon has no atmosphere, no weather, no erosion. Craters there last billions of years, unchanged, preserved in airless vacuum. Mars sits between extremes, more erosion than the Moon, less than Earth. So you see ancient craters, but they're often degraded, softened. The really old ones are just faint, circular depressions, ghosts of impacts long ago. Younger craters are sharper, better preserved. Some even show rays of ejected material radiating outward. These are recent impacts, geologically speaking, within the last few million years. Fresh enough that erosion hasn't erased them yet. Studying crater populations tells scientists about Mars' geological history, when erosion was more intense, when it slowed, how the climate changed. Each crater is a time marker, and their preservation state reveals how active the surface has been. Mars may look dead now, but its surface is constantly changing, slowly, subtly. Wind reshaping dunes, frost sublimating, dust settling and lifting. Nothing stays the same, not even stone. The Spirit rover got stuck in soft soil, but continued doing science. The Spirit landed on Mars in January 2004, Opportunity's twin. For years, it explored the Columbia Hills, finding evidence of ancient hot springs, volcanic rocks, minerals altered by water. Then, in 2009, disaster struck. Spirit was driving through an area called Troy. The soil looked normal, but beneath the crust, it was powder fine. The rover's wheels broke through, sank deep. Spirit became stuck. Engineers tried everything to free it, driving forward, backward, wiggling the wheels. But the sandy soil just flowed around the tires. The more Spirit struggled, the deeper it sank. Eventually, they had to stop. Too much strain on the motors. Spirit was immobilized. But the mission wasn't over. The rover still had working instruments, cameras, spectrometers, a robotic arm. Engineers repositioned the solar panels as much as possible, tilted them toward the sun. Spirit became a stationary science platform. It studied the soil it was stuck in, found it rich in silica, evidence of past hydrothermal activity, hot water flowing through the ground, creating deposits, potentially habitable environments. Spirit operated in this stationary mode for months, through a Martian winter. But without the ability to drive to a sun-facing slope, the rover couldn't generate enough power. As winter deepened, power levels dropped. In March 2010, Spirit sent its final transmission, then went silent. Engineers tried to re-establish contact, but the rover never responded. Its mission ended not from mechanical failure, but from bad luck. One patch of treacherous soil. Still, Spirit gave us years of science, survived far longer than designed, and even in its final months stuck in sand, it kept working, kept discovering. A fitting end for a rover that never gave up. The Red Planet has inspired countless works of fiction and speculation. Mars has fired human imagination for centuries, long before spacecraft, before telescopes even. The ruddy light in the sky sparked stories. When telescopes revealed surface features, people saw canals, networks of lines crisscrossing the planet. Astronomer Percival Lowell became convinced these were artificial, built by an advanced civilization. He wrote books, drew maps, promoted the idea of Martian engineers fighting a dying world. The canals turned out to be optical illusions, tricks of light and imperfect lenses. But the idea stuck. Authors ran with it. H.G. Wells wrote War of the Worlds, invading Martians with heat rays and tripod machines. Edgar Rice Burroughs created John Carter, a Civil War veteran mysteriously transported to Mars, finding a world of cultures, battles, romance. Ray Bradbury wrote The Martian Chronicles, elegant stories about human colonization, the ghosts of Martian civilization. Later authors continued the tradition. Kim Stanley Robinson's Mars Trilogy, detailed visions of terraforming, political struggles, settlement. Andy Weir's The Martian, a Robinson Crusoe story set on Mars. Survival through science and determination. Movies, television, video games. Mars appears everywhere. It's humanity's favorite planet, the one we dream about, visiting, settling, making a second home. That dream drives real missions now. Engineers designing habitats study science fiction, looking for ideas. NASA promotes Mars exploration with posters that echo vintage travel advertisements. Visit Mars, see Olympus Mons. Fiction and reality feed each other. The red planet remains our greatest inspiration, a canvas for dreams, a destination that feels almost within reach. The ExoMars missions aim to search for signs of past or present life. Europe and Russia partnered on an ambitious Mars program called ExoMars. The goal is simple but profound. Search for life, past or present. The program includes an orbiter already at Mars, studying atmospheric gases, mapping water ice, and a rover, Rosalind Franklin. Named after the scientist who helped discover DNA's structure, this rover carries a drill capable of reaching 2 meters underground, deeper than any Mars rover before. Why drill so deep? Because radiation bombards the Martian surface, breaking down organic molecules, making it difficult to find biosignatures. But underground radiation can't penetrate. Organic molecules might survive. Preserved in rock or soil, protected from the harsh environment above, Rosalind Franklin also carries a sophisticated laboratory, instruments designed to detect incredibly faint traces of organic chemistry, to distinguish biological signatures from geological ones, to analyze samples in detail. The mission has faced delays, technical challenges, political complications, but it remains a priority. Because drilling deep into Mars could answer fundamental questions. Is there life now in the subsurface? Did life exist billions of years ago when conditions were better? Or has Mars always been sterile? The ExoMars program represents international cooperation in planetary science. Different nations, different space agencies, united by curiosity, by the desire to know if we're alone. Every mission to Mars is a step closer to answering that question. And ExoMars, with its drilling capability, might take one of the biggest steps yet. Astronauts traveling to Mars would face significant radiation exposure. One of the greatest challenges for human Mars missions is radiation. In space between Earth and Mars, there's no atmospheric protection, no magnetic field. Cosmic rays and solar particles stream freely through the void. Astronauts in transit would be exposed to radiation levels far higher than on Earth. Over a 6 to 9 month journey, that exposure accumulates, increasing cancer risk, potentially causing acute radiation sickness if a major solar storm occurs. Shielding helps, but mass is expensive. Every kilogram of shielding is one less kilogram of supplies, or equipment, or fuel. So spacecraft designs balance protection with practicality. Water, food, fuel, all provide some shielding. Sleeping quarters might be positioned in the center, surrounded by supplies. On Mars, the surface offers some protection. Regolith, rocks, lava tubes, habitats could be built underground or covered with Martian soil. Several feet of dirt blocks most radiation. But astronauts working outside would still be exposed. Spacesuits don't provide much shielding. EVAs would need to be limited, scheduled carefully. Radiation monitoring would be constant. Crews would track their exposure, stay within safe limits. Long-term settlement would require serious infrastructure, thick-walled habitats, extensive underground facilities, maybe artificial magnetic fields, technologies we don't have yet. The radiation challenge doesn't make Mars impossible, but it does make it dangerous. Requires careful planning, advanced technology, and brave people willing to accept the risks, because the human drive to explore often outweighs the dangers. Growing food on Mars would require controlled environments and imported nutrients. Imagine trying to farm on Mars. The soil is toxic. Perchlorates, remember. The atmosphere is unbreathable. Thin, mostly carbon dioxide. Temperature swings from warm to freezing every day. Radiation pours down constantly. Nothing grows in those conditions, so farming would happen indoors, in greenhouses. Pressurized, climate-controlled. Using artificial light or carefully filtered sunlight, the soil would need treatment, washing out perchlorates, adding nutrients. Earth soil contains organic matter, nitrogen, microbes, all essential for plant growth. Martian regolith has none of that. Early colonists would need to bring nutrients or manufacture them, perhaps composting waste, growing nitrogen-fixing bacteria, building soil fertility from scratch. Over time, closed-loop systems might develop, plants producing oxygen, astronauts breathing that oxygen, producing carbon dioxide, plants using that CO2 for photosynthesis, waste recycled into fertilizer, water reclaimed from humidity and wastewater, each component feeding the others. But establishing such systems takes time, infrastructure, knowledge. Early missions would rely heavily on supplies from Earth, supplemented by whatever they can grow. Leafy greens, maybe. Fast-growing crops. Later, as systems mature, the variety might expand. Tomatoes, peppers, grains. The dream is eventual self-sufficiency, growing everything needed to survive. No longer dependent on Earth. That dream is far off, but it's achievable. Plants are remarkably adaptable. With the right environment, they'll grow, even on Mars. Mars' lower gravity might create challenges for long-term human health. We've talked about Mars' gravity being 38% of Earth's. That feels liberating initially. Easy movement, high jumps. But over months or years, it might cause problems. Astronauts on the ISS experience bone loss, muscle atrophy, cardiovascular deconditioning, all from zero gravity. Mars has some gravity, more than none. But is it enough? We don't know. No one has lived in partial gravity for extended periods. The data doesn't exist. It's possible that 0.38 g is sufficient, that bones and muscles maintain themselves reasonably well with exercise, proper diet. Or maybe it's not enough. Maybe colonists would still experience deterioration, just slower than in 0 g. If that's the case, anyone spending years on Mars might face challenges returning to Earth. Their bodies adapted to Martian gravity. Earth's full gravity crushing, overwhelming. They might need extensive rehabilitation, or perhaps they'd never fully readjust. This uncertainty affects mission planning. How long can someone safely stay on Mars? Can they return to Earth afterward? Or would Mars become a one-way destination? Not because of lack of technology, but because of biology. Some scientists propose rotating habitats on Mars, spinning structures that create artificial gravity through centrifugal force, at least for sleeping or exercise, maintaining bone and muscle health. These designs are speculative, complex, but they might be necessary. We simply don't know yet. The only way to find out is to send people, study them, see how their bodies respond. Each mission provides data, refines our understanding, until eventually we know what's safe and what's not. Water on Mars could be split into hydrogen and oxygen for fuel and life support. One of Mars's greatest resources is water, frozen into the ground, locked in polar caps, possibly liquid in subsurface aquifers. For future colonists, water means survival, drinking, irrigation, hygiene. But water is more than just H2O. It's also rocket fuel. Through a process called electrolysis, you can split water into hydrogen and oxygen. Electricity runs through water, breaks the molecular bonds. Hydrogen gas bubbles off one electrode, oxygen off the other. Collect and compress those gases, and you have propellant, liquid hydrogen and liquid oxygen, the same combination that powered the space shuttle, extremely efficient, high energy, and producible on Mars. This is crucial because launching from Mars requires fuel, a lot of it. Bringing all that fuel from Earth would be impractical, too much mass, too expensive. But making it on Mars from local water changes everything. Astronauts could land with minimal fuel, just enough for the descent, then spend months producing propellant for the return trip, using solar panels or nuclear reactors for power, processing Martian ice, filling tanks slowly. When it's time to leave, they'd have a fully fueled rocket ready for launch. This concept is called in situ resource utilization, ISRU, using what's available locally instead of hauling everything from Earth. It makes Mars missions feasible, reduces cost, increases safety. You don't have to gamble on bringing enough fuel for the round trip. You make it there, using the planet's own resources. Mars provides, if we're clever enough to use what it offers. Dust is a persistent problem for Mars exploration equipment. Everything on Mars gets covered in dust. Rovers, landers, solar panels, instruments. The dust is everywhere, fine as talcum powder. Electrostatically charged, it clings to surfaces, accumulates in joints, clogs mechanisms, dims solar panels, reducing power. NASA engineers have struggled with dust since the first Mars missions. Viking landers saw their thermal blankets coated. Pathfinder's solar panels lost efficiency over time. Spirit and Opportunity both dealt with dust accumulation. Their missions would have ended much sooner, if not for fortuitous dust devils cleaning the panels. Dust affects everything. It scratches optical surfaces, gets into seals, wears down moving parts. Future human missions will face the same challenge. Astronauts returning from EVAs will bring dust inside, on suits, on equipment. That dust is abrasive, potentially toxic. It'll get into air filters, food, water. Living with Martian dust will require constant vigilance. Airlocks with vacuum systems, brushes, cleaning protocols. Suits designed to minimize dust entry. Some engineers have proposed electrostatic systems using charged surfaces to repel dust, or acoustic cleaning, vibrations that shake dust loose. Others suggest simply designing for dust. Make everything robust enough to handle it. Seal critical components. Use covered solar panels that can be wiped clean. Whatever the solution, dust will be part of daily life on Mars. An annoyance, a hazard, something colonists will have to accept and manage. The red planet doesn't let you forget it's there. It clings to everything, a constant reminder of the alien environment. The first humans on Mars will likely arrive in the 2030-something decade. When will we send people to Mars? NASA aims for the late 2030-something decade. Other space agencies and private companies have similar timelines, some more ambitious, some more conservative. The technology largely exists: rockets capable of reaching Mars, life support systems for the journey, habitats, but integrating everything, testing, training, building the infrastructure. That takes time and money, lots of it. The first crew will probably be small, 4 to 6 astronauts, carefully selected, trained for years. They'll need expertise in multiple areas: engineering, medicine, geology, biology. Because help from Earth will be delayed, radio signals take between 4 and 24 minutes one way, depending on the positions of Mars and Earth. That means no real-time assistance, no mission control guiding every decision. The crew will be on their own, making choices, solving problems, relying on each other. The mission will likely last around 3 years. 6 to 9 months getting there, 18 months on the surface waiting for the planets to align for the return trip, 6 to 9 months coming home. That's a long time away from Earth, isolated, in constant danger. The psychological challenges might be as difficult as the physical ones, but the rewards are enormous. First, footprints on another planet, discoveries that could reshape our understanding of life, the universe, ourselves. The people who make this journey will be remembered forever, their names in history books, alongside explorers who crossed oceans, climbed mountains, ventured into unknown lands. Mars awaits, and soon, relatively speaking, we'll finally answer it in person. Mars may hold answers to fundamental questions about life in the universe. Why do we keep going back to Mars? Why send mission after mission, spend billions of dollars, devote decades of effort? Because Mars might tell us something profound, whether life exists beyond Earth. That question has haunted humanity since we first looked up and wondered, are we alone? Is life common in the universe? Or are we a cosmic accident, a singular miracle? Mars is our best chance to find out. It's close. We can reach it with current technology. And it had water, organic molecules, energy sources, all the ingredients life needs. If life arose on Mars independently from Earth, then life must be common, spread throughout the galaxy, on countless worlds. But if Mars is dead, always was dead, that tells us something too. Maybe life is rare. Maybe Earth is special. Maybe we're more alone than we hoped. Either answer changes everything, shapes how we see our place in the cosmos. So we search, we drill, we sample, we analyze, looking for evidence, any sign that life once existed or still exists, waiting underground, holding on in some sheltered pocket. Every mission is part of that search. Every discovery adds to our understanding. Mars isn't just a destination, it's a question. And we won't stop asking until we have an answer. Because knowing whether we're alone might be the most important thing humanity ever learns. And so, dear listener, our journey across the rusty deserts and ancient valleys of Mars comes gently to a close. We've wandered together through dust storms that swallow whole hemispheres and stood beneath butterscotch skies streaked with blue sunsets. We've traced the paths of long-dead rivers and imagined water pooling in crater lakes where life might have once stirred. We've climbed impossibly tall volcanoes and descended into canyons that would swallow continents. From the frozen poles with their layered history to the hidden ice buried in mid-latitude plains. From the tiny helicopters proving that flight is possible to the patient rovers still searching for answers in ancient stone, Mars has revealed itself to us. Not as the war god of ancient myth, but as something more compelling. A world that was, that might have been, and that might yet become. A neighbour that challenges us to reach further than we've ever reached before. The red planet reminds us that worlds change, that atmospheres can be lost and regained, that rivers flow and then run dry, that life might emerge and vanish, leaving only whispers in rock. It shows us both the fragility of habitability and the resilience of exploration. Every machine we've sent there, every image returned, every sample analyzed, all of it is part of a conversation stretching across millions of miles. A dialogue between two worlds, one asking, one slowly answering. As you rest here, imagine yourself standing on that rusty surface. The sun smaller in the sky than you're used to. The horizon closer because Mars is a smaller world. The temperature dropping rapidly as evening approaches. Two moons racing overhead in their strange backward dance. Dust settling everywhere in the stillness. And above all that thin atmosphere, the stars, brighter than you've ever seen, undiminished by thick air or city lights. Among them, a pale blue dot. Earth. Home. Impossibly far, yet still visible. Still there, Mars waits for us in that patient, dusty silence, holding its secrets, guarding its past, ready to teach us about planets and possibility, and perhaps about ourselves. It waits as it has waited for billions of years, as it will wait a while longer until the day we finally arrive to walk its surface, to breathe its captured air inside domed cities, to grow food in its soil and draw water from its ice, to make it not just a destination but a home. Until that day, Mars remains what it has always been, a dream, a question, a world just beyond our reach, close enough to see clearly, far enough to remain mysterious. And as your thoughts drift now into stillness, into the quiet space between waking and sleep, let Mars fade gently into the background. Let its canyons and volcanoes blur softly into shadow. Let the butterscotch sky deepen into darkness, and let yourself fall, slowly, softly, into rest, into dreams, into the vast patient silence where planets turn and dust settles and time moves at its own unhurried pace. Close your eyes, breathe deeply, and drift away, into sleep, into stillness, into the gentle, endless dark where the red planet waits. Good night. The Viking landers were the first spacecraft to successfully operate on Mars for extended periods. In 1976, two identical spacecraft touched down on Mars, Viking 1 and Viking 2. They were massive for their time. Each lander weighed over half a ton, carried cameras, weather stations, seismometers, and most ambitiously, biology experiments designed to search for life. The landers scooped up Martian soil, mixed it with nutrients, watched for signs of metabolism, of growth, of respiration. The results were confusing. Some tests showed what looked like biological activity. Others contradicted that. Scientists debated for years. Eventually, most concluded the results were chemical, not biological. Reactions between Martian soil and the test compounds. But the ambiguity taught valuable lessons. That searching for life is complicated. That we might not recognize it when we see it. That our tests need to be broader, more sophisticated. Viking 1 operated for over 6 years. Viking 2 for nearly 4, far exceeding their design lives. They photographed sunrise and sunset, measured winds and temperatures, watched frost form and disappear. They showed us Mars up close for the first time. Not just orbital views, but the ground itself. Rocks, soil, horizon, sky. These images captivated the world. Mars wasn't just a distant red light anymore. It was a place, real, tangible, somewhere you could imagine standing. Viking paved the way for everything that followed. Mars' axial tilt varies more dramatically than Earth's over long timescales. Earth's axial tilt stays relatively stable, wobbling slightly but kept in check by the Moon's gravitational influence. Mars has no large moon. Phobos and Deimos are too small to stabilize the planet's rotation, so Mars's tilt swings wildly over timescales of hundreds of thousands to millions of years. Right now, it's about 25 degrees. Similar to Earth, but calculations show it has varied from about 15 to 35 degrees, maybe even more extreme in the distant past. When the tilt is low, Mars's poles stay cold. Ice accumulates there. The equator receives more consistent sunlight. When the tilt increases dramatically, the poles receive more sunlight during summer. Ice sublimates, gets transported toward the equator. Climate becomes chaotic. Dust storms more frequent. These variations create climate cycles far more extreme than Earth's ice ages. Mars experiences climate swings that completely redistribute water ice around the planet, reshape atmospheric circulation, alter dust patterns. The planet doesn't have one climate, it has many, cycling through them over deep time. Understanding this helps scientists interpret what they see. Those mid-latitude ice deposits, likely remnants from high tilt periods, the layered polar deposits, records of these cycles. Mars' climate is dynamic on timescales we can barely comprehend. And it's all because of orbital mechanics and the absence of a stabilizing moon. The Martian day-night cycle would feel familiar to human colonists. Among all the ways Mars differs from Earth, one thing would feel comfortably familiar: the rhythm of day and night. With sols only 37 minutes longer than Earth days, human circadian rhythms wouldn't be too disrupted. You'd wake with sunrise, work through the day, rest as darkness fell. The pattern would feel natural, not like living on a moon with 2-week-long days and nights, or rotating space stations with 90-minute cycles. Mars offers a human-scale day. This is psychologically important. Studies of isolated groups show that maintaining normal day-night rhythms helps mental health. Disrupted sleep patterns lead to problems: depression, cognitive impairment, interpersonal conflict. Mars colonists would avoid those issues. They could live by a clock close enough to Earth, time that it wouldn't feel alien. Children could grow up with normal sleep schedules. Agriculture could follow familiar patterns. Work shifts could be organized like they are on Earth. The 37 extra minutes would gradually shift local time relative to Earth time. Over weeks, Mars noon would drift compared to Earth noon. But locally, on Mars itself, the rhythm would remain constant, predictable, comfortable. This might seem like a small thing, but for people living millions of miles from home, surrounded by a hostile environment, sometimes small familiarities matter most. A day that feels like a day. A sunrise that arrives when expected. The simple comfort of routine in an extraordinary place. Solar panels are less efficient on Mars due to distance from the Sun and dust. Mars orbits about 50% farther from the Sun than Earth does. That extra distance means sunlight is weaker. The intensity drops according to the inverse square law. At Mars's distance, solar energy is roughly 43% of what reaches Earth. Solar panels there generate less than half the power they would here. Add in dust accumulation and efficiency drops further. Even partially dusty panels lose significant output. This is why rovers and landers need large solar arrays. Spirit and Opportunity had panels that looked oversized for their small bodies, but they needed every square inch to generate sufficient power. And even then, Martian winters were challenging. Shorter days, sun lower in the sky, less power generation at the exact time when cold temperatures required more heaters to keep electronics alive. Some missions have used nuclear power instead. Curiosity and Perseverance both carry radioisotope thermoelectric generators, RTGs. They run on radioactive decay. Plutonium-238, slowly decaying and producing heat. Thermoelectric converters turn that heat into electricity. RTGs work day and night. Don't care about dust or sun angle. Provide steady, reliable power for years. But they're expensive. Require special materials. And not every mission can get one. So most spacecraft still rely on solar. And that means dealing with reduced efficiency. Large arrays. Dust cleaning strategies. Careful power management. For future colonies, solar could still work. Large arrays spread across the surface. Maybe automated systems to clean them. Or covered panels with transparent protective layers that can be wiped, combined with energy storage, batteries, or other systems to get through the night. Mars won't make solar power easy, but with enough engineering, it's manageable. Crewed missions will require redundant life support systems. Sending humans to Mars means keeping them alive for years, in an environment that's actively trying to kill them. No breathable air, extreme temperatures, radiation, isolation. Life support systems have to work perfectly. And since perfection is impossible, they have to be redundant. Backups for the backups. Consider oxygen. You need to generate it continuously, either from stored supplies or by splitting water or processing CO2 from the Martian atmosphere. If that system fails, everyone dies within minutes. So, you have multiple systems, different technologies, independent backups, same with water recycling, temperature control, pressure maintenance, food production. Every critical system needs redundancy, but redundancy adds mass, complexity, cost. Engineers have to balance safety with practicality. How many backups are enough? How much can you afford to carry? The International Space Station has taught valuable lessons. Systems fail. Sometimes in unexpected ways. Redundancy saves lives. But even ISS has Earth nearby. Supplies can be delivered in hours, if needed. Mars colonists won't have that luxury. If something breaks, they're on their own, with whatever spare parts and materials they brought. This drives mission design toward modular systems that can be repaired, common parts across different systems. Creative, problem-solving capability. Because eventually, something will fail, and the crew will need to fix it with whatever they have. MacGyver-style engineering won't be optional. It'll be survival. Ancient riverbeds show Mars once had a hydrological cycle. The dry channels carved into Mars tell a story beyond simple floods. Some show tributary patterns, dendritic networks, smaller channels feeding into larger ones, just like river systems on Earth fed by rainfall. This suggests Mars once had weather, clouds, precipitation, a complete water cycle. Water evaporated from lakes or seas, rose into the atmosphere, condensed into clouds, fell as rain or snow, flowed downhill, collected in streams and rivers, returned to lakes, evaporated again. The cycle repeating. This requires a thick atmosphere, one dense enough for rain to fall without evaporating mid-descent, warm enough that water stays liquid, protected enough that solar wind doesn't strip it away. Ancient Mars must have had all of this for thousands or millions of years, long enough to carve those extensive river valleys, to create complex drainage patterns, to shape the landscape through erosion. Then something changed. The atmosphere thinned, temperatures dropped, rain stopped falling, rivers dried up. The water froze into the ground or escaped to space. the hydrological cycle shut down. Mars transformed into the desert world we see today, but the riverbeds remain, fossils of flowing water. Evidence of a time when Mars was more like Earth, when weather happened, when clouds drifted overhead, when the sound of running water might have echoed through valleys, now silent and dry. Certain regions on Mars show recurring patterns that suggest recent flowing water. Beyond the recurring slope lineae, there are other hints of modern water activity. Gullies on crater walls, fresh-looking, with sharp features suggesting recent formation. Some appear to change between images taken years apart, growing longer, showing new deposits. The timing correlates with seasonal warming. When temperatures climb above freezing, scientists debate what causes these changes. Is it liquid water, briny flows, or dry processes, sand and dust avalanching down slopes? The evidence remains inconclusive, but the seasonal timing is suggestive. And some gullies appear in locations where ground ice might exist just beneath the surface, where a little warmth could melt ice, create temporary flows, brief moments when liquid water exists, before refreezing or evaporating. If these gullies involve water, even occasionally, it means Mars is more active than we thought. That water doesn't just sit frozen underground. It moves, responds to seasons, participates in surface processes. For astrobiologists, this is exciting, because where there's liquid water, even temporarily, there's potential for life. Microbes might survive in frozen soil, become active when moisture appears, reproduce, then return to dormancy. Life on Mars might not be extinct, might not be deep underground. It might be in the soil near these gullies, waiting for the right conditions, living on the edge of possibility. Mars has been observed from Earth for thousands of years. Long before telescopes, humans watched Mars. Ancient Babylonian astronomers tracked its motion carefully, recording positions, predicting where it would appear. Egyptian priests noted its movements, associating it with various gods. Greek astronomers called it Ares, included it in their models of celestial mechanics. Chinese astronomers called it Fire Star, incorporated it into their astrological systems. For all these cultures, Mars was special. Its red color, its brightness, the way it moved across the sky in retrograde loops as Earth overtook it in orbit. When Galileo pointed his early telescope at Mars in 1610, he saw a small reddish disk, not much detail. Later, observers with better telescopes saw more: surface markings, polar caps that grew and shrank, features that seemed to change. In the late 1800s, Schiaparelli in Italy described channels, or canali, crossing the surface. This word was mistranslated as canals, implying artificial construction. The idea captured imaginations. If there were canals, there must be engineers, a civilization. The speculation ran wild until better telescopes revealed the canals were illusions. But Mars had already become the planet most associated with life beyond Earth. That association persists today. Even though we know better, even though Martian life, if it exists, is probably microbial, Mars remains special. The planet we watch most carefully, the one we care most about. Thousands of years of observation leading to spacecraft, rovers, plans for human missions. Our relationship with Mars is ancient and ongoing. Sunlight on Mars is noticeably dimmer than on Earth. Stand on Mars at midday and look around. Everything would seem slightly dimmer than you expect. Not dark, but muted, like wearing light sunglasses. The Sun at Mars's distance provides only about 43% as much light as it does on Earth. This affects more than just solar panels. It affects photography, vision, plant growth. Cameras need longer exposures or higher sensitivity. Human eyes would adapt, but colors would seem less vivid. Plants would grow more slowly, need longer days under artificial lights to compensate. This dimness would be most noticeable to new arrivals. People fresh from Earth would find Mars gloomy, but over time you'd adjust, your eyes compensating, your brain recalibrating what normal brightness means. Colonists who spent years on Mars might find Earth blindingly bright when they returned, squinting in sunlight that once seemed normal. This is one of those subtle differences, not dangerous. Not a major engineering challenge, but psychologically significant. Light affects mood, health, circadian rhythms. Living under a dimmer sun might require artificial lighting, not just for tasks, but for well-being. Bright interior spaces, full-spectrum lights mimicking Earth sunlight, giving colonists the light their bodies crave. Small comforts that make an alien world feel more like home. Mars missions must carefully avoid contaminating areas where water might exist. Every spacecraft sent to Mars undergoes rigorous cleaning, sterilization, testing, to ensure it doesn't carry Earth microbes. This planetary protection is mandated by international treaty. The goal is twofold. First, prevent contamination of Mars. If we accidentally seed Mars with Earth bacteria, we might destroy any native Martian life. Or make it impossible to tell what's indigenous versus what we brought. Second, prevent back contamination. If we bring Martian samples to Earth, we must ensure they don't contain hazardous organisms. Unlikely as that seems, the protocols are especially strict for missions targeting areas where liquid water might exist. Special regions, they're called. Places where Earth microbes might actually survive and grow. Spacecraft going to those areas require extra sterilization, sometimes heat treatment, sometimes radiation, making sure every surface is clean, every component sterile. This adds cost, complexity, time, but it's necessary. The search for life on Mars depends on knowing that any life we find is Martian, not terrestrial. We can't answer the question, are we alone, if we contaminate the evidence. So we're careful, painfully careful, accepting the burden of extra work, because the potential discovery is too important to risk. If we find life on Mars, we need to be absolutely certain it's really from Mars.